Algebra 2, one of 3 students. Today we're going to go ahead and start off taking a look at our calendar and then kind of project out what the week is going to look like. So I'm in the Remote Chapter 5 section. I'm in the Calendar page. You can see here for today, for example, we're going to be doing our check-in, which is really what this entails now, looking at it and just seeing what's going on. Collaboration space video lesson with Q&A included. I'm going to give you guys a lesson in section 5.1 today. I'm going to show you guys where you can give me a set of questions and answers with regards to my notes. Today we're pretty much just going to go through the process of taking notes, and on page 5 and 6 we'll get through as much as we can. So without further ado, here's section 5.1. Okay, so let's treat this like a day 1 lesson on section 5.1. Now, if you take a look at the very top, this right here is a PDF that I've embedded in which you guys can print off such that you can take notes at home. If you can't print it off, simply get out a piece of paper and pencil and just write down what we're doing here today. You can do that in advance of the notes beginning, which is totally fine. You can obviously pause whenever you feel the need to. Just so you can kind of see real quick what that looks like, I'm going to open it up. And it takes you to this PDF file, and you can see, again, you could print that off. You could even, if you want, print it to OneNote so that you can write on it, although that's maybe something that we can set up for you guys separately. All right, so let's take a look. Section 5.1. So graphing quadratic functions. Let's reflect back to Algebra 1. Back in Algebra 1, when we worked with quadratic functions, we noted that a function defined by an equation of the form f of x or y equals ax squared plus bx plus c, where a cannot equal 0. If a does equal 0, then this first term in its entirety is gone, and all you have would be bx plus c. So you do need to have an a value that's not 0. When you're graphing a quadratic function, it will end up being a parabola with these characteristics. You'll have a y-intercept of which is just c, the axis of symmetry, which is just x equals negative b over 2a, and then an x-coordinate of the vertex, simply again, but negative b over 2a, just as that particular x. It turns out the axis of symmetry is a line, while the x-coordinate of the vertex is just, well, an x value of the point x comma y. Let's take a look. Example, find the y-intercept, the equation of the axis of symmetry, and the x-coordinate of the vertex for the graph of f of x equals x cubed minus 3x plus 5. Use this information to graph the function. Okay, so right off the bat, they've noted that a is equal to 1, which I agree. B is negative 3, and c is 5. So the y-intercept is simply just 5. And we've seen that in the past with pretty much any function in which you have an x-intercept or a y-intercept that you can calculate by plugging in 0 for whatever you're not trying to find. So if you're trying to find the y-intercept, plug in 0 for x. If you're trying to find the x-intercept, plug in 0 for y. Okay, so that's simple. Plugging in 0 for for x, so that this first term, a times 0, essentially is just 0, minus 3 times 0, or b times 0, that's also 0. So again, the y-intercept is 0, comma 5. The equation of the axis of symmetry is as such. X equals negative b over 2a. Let's think about this. B is negative 3. So negative of a negative 3, well, that ends up being a positive. So you got 3 over 2 times a. In this case, again, a, because it's 1, that's simply just 2 times 1, or 2. The x-coordinate of the vertex is then 3 halves. And that then speaks to this. I'll use v for vertex in most cases. So let's go ahead and highlight as such, 3 halves comma something. As it turns out, you're going to be able to make a table of values for x near 3 halves, which is kind of what you see here, where in the middle you've got your vertex. I'll use v for vertex again. And simply they've plugged it in. So if you plug in 3 halves for x into the original, you get 3 halves quantity squared minus 3 times the quantity 3 halves plus 5, and you end up with 11 over 4. So this ordered pair right here on the graph go ahead and plot that, is in fact, well, your vertex. So 3/2, comma 11/4. The 2 points that I would argue are smart to choose, and then in fact get an easy representation of the graph would be a value of which is the same number of units left and right of the vertex. So 0 is nice, and we already saw that 0, comma 5 is the y-intercept. And if you go 1.5 not left of the vertex, but 1.5 right of the vertex, you're going to see here the y value the same for that particular point. And those additional 2 points that are devised here, that's fine. I only require my students to find 3 points. So 0, 5, which we already knew, the vertex 3/2, comma 11/4, which we calculated after doing negative b over 2a, and then plugging it in, like I said, to get 11/4, and then 3, comma 5. Let's plot those points. So here's 0, 5. Here's 3, 5. Okay, there's a line that you see, this dashed line, which technically represents something called axis of symmetry. I'm going to abbreviate AOS for axis of symmetry, and I'm going to write x equals 3/2. So the axis of symmetry will always cut the parabola in half and give you that symmetric kind of look. So that points equidistant from that line, left and right, namely 0, 5 that we used, and also 3, 5. 0, 5 is 1.5 units left of the axis of symmetry, and 3, 5 is 1.5 units right. And then, of course, you've got yourself your parabola takes shape through those 3 points. Every parabola, generically speaking, takes shape as this kind of U-shaped curve. It doesn't necessarily have to open up. We'll also see parabolas that open down. Let's take a look at an example. We'll do problem number 1. It says, again, complete parts A through C for each quadratic function. For part A, find the y-intercept, the equation of the axis of symmetry, and the x-coordinate of the vertex. B, make a table of values that includes the vertex. And lastly, use this information to graph the function for part C. Okay, so for number 1, we've got an A value of 1, we've got a B value of 6, and a C value of 8. So to find the y-intercept, you simply look at C and note that when x is equal to 0, no matter what A or B happen to be, plugging in 0 yields 0 overall. So literally all you have to do is note that the C value is really your y-intercept. It also asks for the equation of the axis of symmetry, which I'll write down here, AOS. So negative b over 2a, and I'm going to actually write x first. Sorry, x equals negative b over 2a. So we're looking at negative 6/2 or negative 3. That's nice. So we've got our axis of symmetry at negative 3. That's going to set us up quite nicely for the graph, of which, when we plot the vertex, we know we're going to have negative 3 in the middle, comma something. And then I would also argue that 0, 8 is a nice point to choose. But let's think about what point is equidistant from the axis of symmetry. Namely, well, if you go 3 units right of negative 3, you're at 0. So that would then mean what? 3 units left of negative 3, which would be negative 6. That particular x value will yield the exact same y value of 8. Why? Well, remember back in the example up above, we talked about the idea of it being equidistant. If, in fact, you pick a point that is left and right of the vertex, the same distance, the y's are going to end up being the same. So those 2 points have those 2 y's. The x-coordinate of the vertex is negative 3. Let's find the y. That's going to be as easy as plugging it in. So let's do that. So we'll say y. We've got negative 3 quantity squared plus 6 times negative 3 plus 8. So if we do this math, we end up with 9 minus 18 plus 8. 9 minus 18, that of course is negative 9 plus 8, that's negative 1. So my vertex is negative 3, negative 1. 3 points is really all you'll need to graph a parabola. That's all I require. Let's plot -3, 1, 2, 3, -1, 0, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So we're a little bit off the graph, which is fine. We'll deal with that. -3 is here, so -4, 5, 6, and then up also 8. So here's your parabola. Graph it. And there you have it. The axis of symmetry, I've already written it down, but let's go ahead and I'll draw that line that cuts right through. The vertex I usually like to label, so let's do that as well. Okay, so now let's move on to page 6 and see what's in store there. So moving on, it says, continuing, of course, graphing quadratic functions, maximum and minimum values. The y-coordinate of the vertex of a quadratic function is the maximum value or minimum value of the function. So max or min or maximum or min value. The graph of the function, again, where a can't be equal to 0, opens up and has a minimum when a is greater than 0, but it also opens down and has a max when a is less than 0. So determine whether each function has a max or a min value and find that value. Then state the domain and range of the function. Okay, so for part A, here's your equation. Okay, right off the bat, I'm going to highlight that my a value of 3 is in fact positive. And since it's positive, the graph will open up. And the function, therefore, is going to have a minimum value by definition. So picture, if you will, without really knowing exactly what the graph looks like, imagine, if you will, a parabola that opens up. Well, that point down there at the very bottom, that's going to be our minimum, the vertex, of course. That's the minimum because, well, there's no other point that is below that point. The minimum value of the y-coordinate, is the y-coordinate of the vertex. So technically, when we calculate the min value, it'll end up being the y-coordinate of that. So let's find the x-coordinate, just like we did on the prior page. So -b, so negative of a, we'll make a correction here, because negative of a -6 will be +6. So we got 6 over 2 times 3, or 2 times a, so they got 6, 6, which is in fact 1. Evaluate the function at x equals 1 to find the y value, aka now the minimum value. And in doing so, you'll plug in 1, such that f of 1 equals 3 times 1 squared minus 6 times 1 plus 7. Well, the math ends up being pretty nice. 3 times 1, which is 3, minus 6, -3 plus 7, which is 4. So the minimum value of the function is just 4. Then we can speak about the domain and range. Without yet knowing what the graph looks like, and yes, we can even use our graphing calculator to verify, it ends up, as we again knew from the beginning, that it opens up, so the domain and the range we can assess pretty easily from that. The domain is all reals, and the reason is because, well, any x value can be substituted in, any value for x can be substituted in. And then the range will be, well, any number but greater than or equal to 4 technically. As far as interval notation, which is something you have to also be familiar with, this would be the domain. Well, this would be the range. So -infinity to +infinity for what x can be, again, all real, while the range, well, greater than or equal to 4 looks something like this as an interval. For part B, we'll take a look. The function is going to be one where here's your a value. A is -1, so it's going to open down. And in that context, then we can hopefully see that because the parabola opens down, your vertex y-coordinate will not be a minimum, but a maximum value. And again, we're going to look at the y-coordinate of the vertex to justify this. I'll cut to the chase with this. -b over 2a, so negative of a -2 ends up being positive over -2, so that ends up being -1. Plug it in, and they're going to get a value of 101, which of course is the minimum, and your domain and range are as such. All reals for the domain and the range as you see it. This concludes the lesson for section 5.1. Please take a look at our calendar to take on those respective problems that I've assigned.